Right. So, in our course selected topics in decision modeling, we are now in our 24th lecture, that is solving unconstrained nonlinear programming problems. So, that is our lecture, that is solving unconstrained nonlinear programming problem. Now, in our previous lecture, if you recall, we have seen that whether multivariable unconstrained NLP problems, we need to find out the gradient. We put the gradient equal to 0, and from those gradient, we also find out the Hessian matrix. Then we check whether the Hessian matrix is positive definite or negative definite, and based on that we try to find out the maxima or minima of this particular function, right. So, based on the nature of the Hessian matrix. How do we find out the extrema, maxima or minima? By putting the gradient equal to 0. So, let us take some examples and see what kind of difficulties can come while following this procedure. So, here is a function before us, that is f y equal to y 1 square plus y 1 into 1 minus y 2 plus y 2 whole square minus y 2 y 3 plus y 3 square plus y 3. So, if we find the gradient, that is del y 1 for the function, then what are the terms which will be useful here? So, as you can see, that is the first term that will be useful, the second term will be useful, and that is all. So, those are the terms that will be useful. So, in the first term, what you get is 2 y 1, and in the second term 1 minus y 2. So, that is the del y 1 of del f del y 1. For the second term, again what are the terms that will be useful, that is because del y 2. So, it is the second term which will be required, the second term, then the third term, the fourth term, that is all. So, the second term will give us minus y 1, the next term 2 y 2, and here minus y 3. That is a very simple partial differentiation. And for the del y 3, again we see the only the last few terms, that is the last 3 terms will be useful. So, again you see that this term and this term, they will be useful. So, it becomes minus y 2 plus 2 y 3 plus 1. So, when you put them all, we get the gradient matrix, right, del f y 2 y 1 plus y 1 minus y 2 minus y 1 plus 2 y 3 y 2 minus y 3 minus y 2 plus 2 y 3 plus 1. So, that is the gradient, right. So, after the gradient, what we do, we must have the next, that is the gradient should be set to 0. So, that is what we have done here, the gradient is set to 0, that is the first term, basically it means that set the 3 terms equal to 0 separately, right. So, if you set these terms separately equal to 0, then how do you find out the values of y 1, y 2 and y 3. So, it is a very simple problem really. All we have to do is solve a set of simultaneous equations, not much challenge here. So, quickly if you can see, if you add the double of the second term with the first term, then this y 1 gets cancelled, then we get 4, that is 3 y 2, 3 y 2 minus y 3, 3 y 2, see that is what we are doing, we are adding the double of the second term. So, that is 4 y 2 minus y 2, so 3 y 2 minus 2 y 3 plus 1 equal to 0. So, what we have done? We have doubled this and added with the first equation. So, it becomes 4 y 2 minus y 2 3 y 2 minus 2 y 3 plus 1. Now, this and this third equation you can also add. So, if you add, then what do we get? We get 2 y 2 minus, so this one is plus, so this will be plus also 1 and 1 2. So, this will be 0. So, what is the value of y 2? It becomes minus 1, right. So, very quickly we got y 2 equal to minus 1. So, using them, so minus of minus 1 is again plus 1. So, 2 y 1 plus 1. So, from the first equation we get 2 y 1 plus 1 again plus 1 equal to 0. So, y 1 is also minus 1, right. So, we get y 1 is minus 1, y 2 also minus 1. So, put them in the second equation. So, minus of minus 1 is plus 1 and plus 1 minus 2. So, 1 minus 2 minus y 3 equal to 0. That is what you can write from the second equation. So, that gives y 3 also equal to minus 1, right. So, very simple. Just this set of simultaneous equations you can solve and we get y 1, y 2, y 3 all equal to minus 1. So, that is exactly what we have seen here. Those three simultaneous equations are solved and we get y 1, y 2, y 3 that is equal to minus 1 and minus 1. Now, additionally, we have to find out also the Hessian matrix, right. So, you can do that as an exercise. So, I am not doing it here. Supposing we find the Hessian matrix of those things. So, basically this is our gradient. So, that gradient if you really do say actually these are the gradients. So, please look that del f del f del not d del f del x 1 equal to 2 y 1 plus 1 minus y 2. So, if you take one more time sorry not x 1 y 1. So, if you take one more time del y 1, this is written x 1, but they really should be all x y 1. So, if you take them, then it should be the value should be 2, right. So, that will be our Hessian matrix. So, that should be 2, right. So, that is what it is. So, actually this kindly correct this. So, that is what we get, that is going to be our Hessian matrix. Now, once we have found out the Hessian matrix, let us try to find out the eigenvalues. So, eigenvalues again this is our Hessian matrix. So, what we have to do is we have to A minus lambda I equal to 0, that is our characteristic matrix, and this characteristic matrix has to be a characteristic equation. That characteristic equation if you really put, then we get the Hessian matrix minus lambda 0 0 0 lambda 0 0 0 lambda equal to 0. So, we get this matrix 2 minus lambda minus 1 0 minus 1 2 minus lambda minus 1 0 minus 1 2 minus lambda equal to 0. Is it all right? So, that should be equal to 0 to find out the eigenvalues. Now, what it is? Now, this is this one. So, how the multiplication happens? It should be then 2 minus lambda, that is this term, into 2 minus lambda into 2 minus lambda minus minus 1 into minus 1. So, basically that is how we proceed. So, we take this one and this one. So, 2 minus lambda. So, this is this one, and 2 minus lambda into 2 minus lambda minus minus 1 into minus 1, that is the first term. The second term, what will be our second term? The second term will be starting with this, and it should take these terms. But please remember, there is a cofactor, there should be a negative value. So, negative should be thing also. So, that is what has been done in the case of the second term. So, all these are first term, this is first term. Now, in the second term, you see what we have done, we have taken the minus of that is very important, minus 1 into that negative, that usually comes for the second term, minus 1 into minus 1 into 2 minus lambda minus minus 1 into 0, right. And the third term, what will be the third term? The in case of third term, we should take this one and this one. So, plus 0 into dot dot dot, because minus 1 into minus 1 minus 0 into 2 minus lambda, but there is no need to write it, because anything multiplied by 0 will be 0 only, all right. So, when you combine them all, then we get 2 minus lambda can be taken as common, and all of these terms. So, 2 minus lambda into 2 minus lambda. So, it will be 4 plus lambda square minus 4 lambda minus 1, which is coming from here. So, that is minus 1. So, all of these are first term. Then in the second term also, this is our second term. If you see that second term, in the second term, if you take out 2 minus lambda, then this term is 0, then we really have a minus 1 here. So, all that minus 1 will come inside. So, this is 3 minus 1. So, it become 2, and 2 minus lambda can be taken common, right. So, finally, we get this kind of equation, 2 minus lambda, lambda square minus 4 lambda plus 2 equal to 0. Now, this problem was simple. So, obviously, we could easily get into this kind of forms, but in all problems it may not be so easy, but then we have to find out the lambdas by some way or the other, and that is a major challenge for such kind of problems. So, we should remember that, right. Now, once we find out, now this can be factorized. The idea is that this into this is 2. So, 4 should be divided in such a way that the multiplication is 2. So, that is 3.41 and 0.59. So, we have 2 minus lambda, lambda minus 3.41, lambda minus 0.59 equal to 0. So, we have 3 different values of lambda, and those values are 2, 3.41 and 0.59, right. So, we have now the 3 lambda values. So, what is your conclusion about the eigenvalues? The eigenvalues are all found to be positive. So, since all the eigenvalues are positive, the Hessian matrix will be then positive definite, right. We have a positive definite Hessian matrix, and the conclusion therefore is that the point y1, y2, y3 minus 1, minus 1, minus 1 is a minima, right. So, a minima has been found, but is it a global minima? We may not know, because the function has to be convex, or we have to know the shape of the function, right. So, that also is the additional task that is required. Only thing, we found a minima, but it can be a local minima as well, right. So, you see sometimes if the nature of the plot is of this type, suppose we found this point, obviously it is a minima, but look here, there are other minimas as well, and if you look at this, then this point is having a lower value. So, these minima could be a local minima and may not be a global minima, right. So, that has to be remembered. Fine. So, that is how we found out by with the help of the gradient and the Hessian matrix and the eigenvalues of the Hessian matrix, we are able to solve the unconstrained problem. But then there could be some other difficulties. What are they? Let us see. See, what really happens that the gradient we have seen, it was not easy to really put those gradient values and put to zeros and then finding Hessian matrix and all those things. So, there should be a procedure where it even if we are not able to put del f x equal to 0, there should be a method by which we can approach and we can do with the help of gradient search itself. So, that is the technique that is called the gradient search procedure for unconstrained NLP. The search procedure keeps moving in the direction of the gradient until it reaches an optimal solution x star, where the gradient equal to 0, right. So, from a current trial solution, procedure does not stop until f x stops increasing, right. So, supposing this procedure is shown for a maximization problem. So, supposing we have a maximization problem and we find a gradient, and then we know that if we go on the direction of the gradient, and at a given point that we have got a gradient value, and we see the f x is increasing, then we recalculate the gradient for a new trial solution for there is a value called x dash, where x dash equal to x dash plus t times the gradient, where t star is the positive value of t that maximize the function at that point, right. So, it is t times the gradient. If you add with the current trial solution value, the functional value at that point we maximize. Is it all right? So, that is how we do, and these f x dash is the current trial plus the t times the gradient is nothing but the f x, where see, please remember this is a multi-valued. So, x is not one variable, it is a number of variables. So, where individual values x j's are x j equal to x j dash plus t times the del f del x j at x equal to x 1. And where do you stop? When the gradient is lower than, for each individual gradient of individual x I j's are less than equal to epsilon, where E is a small tolerance. So, it is a standard gradient search procedure. Basically, we find a current trial solution and we find out the gradient, and we add the gradient with regard to the t and see the functional value at that point, and that we maximize to find t, and then change the x j's in that direction and make it our new trial solution. So, that is the procedure. It will be very clear once you see a problem, then we can revisit this once again if we have some doubt. So, initialization, select an epsilon small value, a trial solution x dash, and choose the stopping rule. Iteration x dash equal to x dash plus t star the gradient at x dash, where t star is the positive value of t that maximize the functional value at that x. Now, express this functional value as a function of t by setting x j equal to x j dash plus t del f del x j at x equal to x dash for each x, and then substituting these expressions into f x. So, that is how the procedure goes. So, how it is? Let us see, and obviously, we have the stopping rule that the gradient, that the partial derivative for each variable should be less than equal to epsilon, and if so, stop with the current x equal to x dash as the desired approximation of an optimal solution, else perform another iteration. So, that is the method. So, once we know the method, as I said, we will revisit the method maybe one more time after we see how a problem is solved. So, supposing we need to maximize a function which is f x, which is where x is basically two variables x 1 and x 2, and the function is 2 x 1 x 2 plus 2 x 2 minus x 1 square minus 2 x 2 whole square, right. So, if you really want a to find this problem and details further, you can see the Hillier-Lieberman book, the operations research, where the problem is solved as well. So, I have taken it from the Hillier and Lieberman book. So, what we do? We first find out the gradients or the del x 1 and del x 2 of the function. So, what will be the del x 1 of the function? Very clear, it should be 2 x 2 minus 2 x 1. And what is del x 2 of the function? That is 2 x 1 plus 2, that will come from here, and from here minus 4 x 2. So, that is the first step, find the gradient, right. So, these two are obtained. So, this part is very clear. Now, go to the next step. So, after that what we do, supposing we arbitrarily start at a point 0 0, we start at a origin, because see if you look at the function, the value of the function is 0 at the origin, right, because x 1 0, x 2 0, the functional value is 0, and if we are going to get a positive value, we assume that we have a positive value which is higher than the 0 value, right. So, that is how we start at the origin. Now, already we found that the partial derivatives and the gradient at this point can be obtained as at this point 0 0. If you put, that is these are our del f del x 1 and del f del x 2. So, if we put x 1 equal to 0 and x 2 equal to 0, then the first value becomes 0 and the second value becomes 2, because x 1 0 and x 2 0, that remains 2, this becomes 2. So, the gradient at this point is 0 2, right. So, we have found the gradient at that given point 0 0, is all right. So, we found the gradient, right. Now, what do we do with this gradient? Now, what we do, see, look here, this is our x 1 and x 2. So, please recall, if you recall, what was our gradient? Gradient was 0 2, right. So, 0 for x 1 and 2 for x 2. Now, the point we started, the trial solution is 0 0, right. So, basically x 1 equal to 0 and gradient for x 1 is 0. Right. So, gradient for x 1 equal to 0 and x 1 equal to 0. Similarly, x 2 equal to 2 and gradient x 1 equal to x 2 equal to 0 and gradient is 2. So, these are the things. Now, if we move in the direction for t distance, then what will be the new value of x 1 and x 2 in terms of t? It should be 0 plus t star 0, that is 0 for x 1, and x2 will be 0 plus t star 2 because gradient is 2 equal to 2t. So, 0 and 2t are the new values for x1 and x2. And what is the functional expression? This is our functional expression. So, if these functional expression value we find out for 0 and 2t, that is our new functional value. So, what it will be? 2 into 0 into 2t plus 2 into 2t minus 0 square minus 2 into 2t whole square. So, this comes to 4t minus 8t square. So, look here what we found. So, graphically if we want to know, then we had a point. So, this side is x1, this side is x2, right. So, we are here, this is our initial trial point 0 0. Now, from 0 0 we have come to a new point which is 0 2 t. Why? Because the gradient is 0 2, 0 for x1. So, we are not moving in that direction, and 2 for the x2. So, we know that if we move in this direction, our functional value is going to go up, and the new functional value in terms of t is 4t minus 8t square. That is all we have found, right. So, I hope you understand. So, now with that knowledge we try to maximize this value, the functional value, because that is all we try to do. How do we do? We differentiate. So, as we differentiate this 4t minus 8t square, we find the 4 minus 16t equal to 0. So, we find a value of t which comes out to be 1 by 4. So, you see how much we move to the direction is is 0 in the x1 direction and 2t in the y x2 direction. How much is 2t? T comes out, t star comes out to be 1 by 4. So, that is essentially exactly what happens, right. So, t comes to be 1 by 4. So, we got current trial 0 0 and t star equal to 1 by 4. So, accordingly, since x j equal to x j star plus t into the the partial derivative at x equal to x dash, and we had 0 and 2. So, x 1 becomes 0 and x 2 becomes half, right. So, it was clear that 1/4 is t and it has moved 2 t, that is what we saw earlier. So, new point has to be 0 and half, right. So, that is our new trial solution 0 and half. So, with that 0 and half we again iterate. So, new trial solution 0 and half. So, again we find partial derivatives. So, we know those partial derivative values. So, this time if I put x 1 equal to 0 and x 2 equal to half, then the partial derivative with respect to x 1 is 1 and partial derivative with respect to the x 2 is 0. So, the new gradient will now become 1 0, that is at that point. So, this time we are not moving towards x 2, we are now moving towards x 1. All right. So, now we have x 1 is 0 plus t star 1 t and x 2 remains at half. So, what happened if you recall, we started at origin, we have come to a point, now we are going in this direction, not earlier we have come in this direction, this was x 1 direction, this is x 2 direction, now we are moving in the x 2 direction, because the although little bit on x 2 also, because x 2 is half, right, and not dependent on x 2. So, it will move slightly this direction, not this direction. All right. So, if you substitute these expression, then the functional value becomes after calculation t minus t square plus half. So, this is going to be our new functional value. So, with this functional value, what we can do further, we find out the functional value becomes maximize of this, and if you differentiate again, then we find T star equal to half. So, what is the significance of this T star equal to half? So, this was our current trial x dash, so 0 and half, T star is half. So, x j values will be, these are our differentials. So, x 1 will be 0 plus half into 1, that is half, and x 2 will be half plus half into 0 equal to half, because at this point these are our the gradients, right. So, that means we are not moving in the x 2 direction, although we got a value in that direction. So, since we are not moving, so new point becomes half and half, right. So, that is a new point that will become half and half. So, all of these are tabulated here in the next table. So, initially we started with 0 0, then we got 0 and half, then from 0 and half we move to half and half. So, if you continue in this fashion, we go to half 3 by 4, 3 by 4 3 by 4, 3 by 4 7 by 8, etc. Alright. So, we go to all these points and it looks like this. So, I was showing you from 0 0 to 0 and half to half and 3 4, 3 by 4 to 7 8, then like this we keep moving, and if you really look at the direction, we are actually moving to 1 1, it is the optimal solution, verified by the fact that del f 1 by 1 is 0 0, because if you move any further, then gradient will fall, that means the curve will be like this, right. So, that is going to be the optimal point. So, really we may not be able to get to the optimal point. So, the note should be the converging sequence of trial solutions never reach its limit, the process actually stops somewhere slightly below 1 1. So, if the objective function were minimize f x, the move should be in the opposite direction of the gradient at each iteration. So, instead of plus it should be minus, and instead of maximizing it should be minimizing, right. So, this is how without really computing the Hessian matrix and eigenvalues, if we cannot do that, then from a gradient value itself we can do a gradient search, right. So, in our next lecture we shall see some more numerical methods for such kind of problems, right. So, thank you very much.